All right, so next up, we're looking at optimization problems, and like I said, we're getting into the heart of calculus here. There's two major. We're building up to two major topics in calculus, and this is the first one, and that's optimization problems. All right, so I'm going to read the guidelines for solving optimization problems, but then we're going to apply them when we get to our examples here. So the first one is we just got to draw a diagram when you can. All right, now the key here is you got to find the quantity that you're either trying to maximize or minimize. So it could be a lot of different things. Then we're going to set up a formula that involves the max or min value in terms of other variables. But if there's too many variables, we're going to have to eliminate them. And so in the end, we want an equation with the variable that we're trying to maximize or minimize and just one other variable. All right, and then what we're going to do is, well, number 5 there, solve using the algorithm for max and min values. So again, that's where we're going to take the derivative, set it equal to 0, and find out where potential max or min values are. All right, and check endpoints if there happens to be some. All right, so on that note, here we go. We start off with an Ennismore farmer has 14 meters of fencing and wishes to enclose a rectangular field. But one side of the field is against a stream and does not need fencing. So the farmer wants to enclose the maximum possible area using all of the fencing. What are the dimensions of the largest possible field? All right, so step 1 here is I'm going to draw a little diagram. All right, so there's my water, and we're building a fence, a rectangular fence. All right, along the water where I'm going to have, I guess, width x. So x on one side, same on the other, and length y. All right, so there is our diagram. All right, so now we get to 2. Find the quantity to be maximized or minimized. Well, in this case, what are the dimensions of the largest possible field? So what we're trying to maximize here is the area. All right, so we need the max of the area. Now in this case, the area of our rectangle is length times width, which in this case would be x times y. All right, now, so that's step 2. So, step 2, we found the quantity. Step 3, we did that. Then we get to step 4. If the formula contains more than one variable other than the quantity that is being maximized or minimized y, we need to find other relationships among those variables so that all others can be eliminated. Your final formula should contain only 2 variables, y, or area in this case, and another variable. So we do have too many variables. We have our max variable, our a, which has got to stay, but then we have an x and a y. So we got to get rid of one of them, looking at some other relationship. Now in this case, there is another relationship, is that I know that this person has 1,400 meters of fencing. And that is in terms of our surface area, or not surface area, our perimeter. And so the perimeter of this object is 1,400 meters of fencing, and the perimeter involves 2 x's, or 2 widths if you want, plus a y. And since y is already by itself here, I'm going to move the 2x over the other side because I want to isolate one of the variables. So I'm going to move that 2x over the other side. It's a minus 2x. And that equals y. Now, the reason I'm doing that is so now I can change my equation up here, my area equation, that I'm trying to maximize the area. And so now what I have is a is equal to, we have the x, but now the y, I'm going to make a substitution here of 1,400 minus 2x. And so now what I have is an area equation, there we go, that just has x's. So now I'm going to simplify this a little bit. So x times 1400, well, that's going to be 1400x. And then minus x times 2x. Well, that's going to be 2x squared. All right. So now we've got an equation. We're trying to maximize area. We have it in terms of one other variable. All right. And so now I'm on number 5 here. Solve the algorithm, or solve for using the algorithm. All right, so that means I'm going to take the derivative of our area, because that's what we're trying to maximize. So a prime, all right, is equal to the derivative of 1400x is just 1400. And then the derivative of negative 2x squared is negative, let's see, 2 times 2 is 4, and subtract 1 from the exponent. All right, so there's our derivative. Now again, to find a max or a min, we're going to set that derivative equal to 0. All right, so that means we got 0 is equal to 1,400 minus 4x. Just put a space there. All right, so I'm going to move that negative 4x over to the other side, so it becomes a positive 4x. And then what I need to do, well, I got to get x by itself here, so I'm going to divide both sides by 4. And so the value of x that gives us a maximum area is going to be 350. Now I can, well, I am going to sub that 350 in right here, because I want to know what the y value is going to be, because I have a formula here for y equals. All right, so I'm also going to find the y value, find the dimensions of this area that gives us the max. All right, equals y. All right, so I follow a little bedmas here. So 1400, 2 times 350 is 700. So y is going to equal 700, and we're talking about meters here. All right, so therefore, we've got our dimensions here. Therefore, I should put the largest field is, our area is equal to length times width, or in this case, 350 times 700, which is equal to 245,000 meters squared. All right, if x is equal to 350 and our y value is equal to 700. And there we go. All right, so I'm going to try another one, a little more complicated, a little bit different. I'm going to throw a couple different scenarios at you here. All right, so we get to example 2. Chris and Jen are both training for a marathon. Chris's house is located 20 kilometers north of Jen's house. And at 9 a.m. Saturday, Chris leaves his house and jogs south at 88 kilometers an hour. At the same time, Jen leaves her house and jogs 6 kilometers east. So I guess she wants no part of Chris. When are Chris and Jen the closest together, given they both run for 2.5 hours? Well outside my range. All right, so again, I'm going to try to draw a diagram. So let's see. They're both training for a marathon. Chris's house is located 20 kilometers north of Jen's house. All right, so in terms of a diagram here, there is Jen's house. So I'll put a bit of a J there. And let's put Chris up here, north. There's Chris's house. All right, now at 9 a.m. Saturday, okay, Chris leaves his house and jogs south at 8 kilometers an hour. All right, so I'm just going to put a little dotted arrow there. So Chris is jogging south at, let's see, I'll put beside his name here. Chris goes at 8 kilometers an hour. All right, now at the same time, Jen leaves her house and jogs 6 kilometers east. All right, so for those of you in my physics class, you know that east, we're going to go to the right here. I'm going to draw that just a little bit bigger. Want a little more room. A little dotted line there. She's headed this way. All right, and again, she is traveling at a rate of 6 kilometers an hour. Okay. When are Chris and Jen closest together, given they both run for 2.5 hours? So our distance between them is ever changing, and that would be from wherever Chris is to wherever Jen is. All right, so that is our distance. That is, okay, we'll get to that. What else we got here? I forgot about this. Chris's house is located 20 kilometers north. So let's put that in. So they start off, that's a fixed rate there, 20 kilometers. All right, now let's check it out. So now the last sentence is, when and Chris or Jen closest together. Closest together. So what we're trying to do here is take our distance and we're trying to minimize it. We want the min of our distance here. All right, now we've got we've got distances, we've got velocities, and we're looking at when, the time, are they closest together. So what I'm going to use here, and again, this is for all you physics people out there, is I've got a relationship between velocity, distance, and time. It's v equals d over t. But because I'm trying to minimize distance here, I'm just going to rearrange this formula where I had d is equal to v times t. And so I've got a triangle here. All right, and to start off, this black, well, let's see, I'll color code them here. So this purple line, if Jen, and I also got a right angle triangle here, that's important. I got a right angle triangle, and I'm saying that because I'm going to use the Pythagorean Theorem here to come up with a formula. So d, I'm going to use d squared. Now this purple line, Jen is moving at 6 kilometers an hour. That's her velocity. And so her total distance would be 6, because that's her velocity, times her time. But since that is a side of a triangle, and I'm using the Pythagorean Theorem, I'm going to square it. Now, the next part is that Chris here is moving at 8 kilometers an hour. All right, so the distances he travels along this black line would be, this, just like Jen, would be 8. That says v times t. That's just the black line, but we're looking for the blue line here. Well, again, there's 20 kilometers between Chris and Jen. And so this blue line would be 20, but take away 8t, whatever distance Chris has traveled. So the blue line here is going to be that 20 kilometers minus however far Chris has traveled, which again is velocity times time. And again, because we're dealing with the Pythagorean Theorem here, we got squared. All right, so there we go. So now I've got my formula. And I'm lucky it's only in terms of one variable, right? We've got, well, sorry, two variables, but we've got the variable we're trying to minimize plus the other variable, one other variable, which happens to be time. All right, now here's what I'm going to do. Before I take the derivative here, which is my next step, I'm going to simplify this equation. And so first off, I got d squared is equal to, let's see, 6t squared, square the 6, square the t. All right, now square, all right, so I got to take 20 squared, that's 400. Then I got 2 times negative 8t times 20. Calculator time. And let's see here, 2 times 8, negative 8t times 20, I get negative 300. and 20t. And then I've got to take negative 8t squared. Well, negative 8 squared is plus 64, and t squared is t squared. All right, now I do have some common like terms, I guess I should say, put together. I can put together a t squared, so I got 36t squared plus a 64t squared. That's 100t squared. All right, then I'm just going to write it in order, minus 320t, and then plus 400. Now, I could do implicit differentiation, because it is time to take the derivative, but I'm not going to do that. I'm going to get square root both sides. So when I do that, that little 2 is gone, and well, then this whole thing would be taken to the 1/2, because that means square rooting. There, so now I got d by itself, all in terms of one other variable, t, and now I can take my derivative. All right, so here we go, d prime, and then I'm going to set it equal to 0. So taking the derivative. All right, so I'm going to have 1/2 down in front, plus what's inside, which is my 100 t squared minus 320t, and then plus 400. Oops. Bracket, I subtract 1 from the exponent. All right, so I'll have to put in the negative 1/2 there afterwards. But then I got a chain rule, because I have a function inside, so I got to take the times the derivative of the inside of this function, and so the derivative of 100t squared would be 200t, and then the derivative of minus 320t is just minus 320, and then the derivative of 400 is 0. And so again, make sure I don't forget, that exponent is negative 1/2. All right, now I'm going to before I set this thing equal to 0, I'm going to rewrite this derivative. All right, so I've got the derivative is equal to, now this big thing up top, this everything in brackets, 100t squared minus 320t plus 400 to the negative 1/2. Again, negative exponent, I'm going to put it in the denominator. All right, so there it is. And the negative 1/2, well, the negative sign, I put it in the, again, in the denominator, and the 1/2 means it's a square root. All right, so I've taken care of that part. Now I got 1/2 times 200t times negative 320. Well, 1/2 times 200t would be 100t. All right, then 1/2 times negative 320, I believe is negative 160, but I better make sure here. Last thing I want to do is mess up. Yep, all right. There we go. Now, here's a good part, is now I'm going to do my algorithm. So I set our d prime, our derivative, equal to 0. Now the best part, when you have a fraction, the only thing you need for that derivative to be equal to 0 is the numerator. So all I'm looking for here is, when does 100t minus 160 equal 0? So I don't have to worry about the denominator, because again, when you got a fraction, for it to be 0, all that has to happen is the numerator equals 0. In our next unit, we'll worry about the denominator, because it will have applications, but not right now. All right, I'm going to move that minus 160 over to the other side. Whoops. Becomes positive, and then the last thing I need to do here is divide by 100 to get t by itself. And so our t value is 1.6 hours. Now what did it ask again? That's when they're the closest together. When our Yes, yeah, that is within 2.5 hours. That's within our interval. Now, I could test out our endpoints. All right, so I got, well, here's our d equation right here. I want to see if I can copy it. There we go. Control C. All right, so if I substitute in my D of 1.6, now just for time, I'll tell you that I subbed it in and did my calculations, and I got 12 kilometers. Now, the other endpoint is, well, 0. How were they when they started out? And, well, if you put a 0 in there, into the equation, I end up getting, well, these two terms, 100t squared and negative 320t become 0, and you get 400 to the 1/2, or the square root of 400, which is 20 kilometers. All right, and then the last endpoint is 2.5 hours. All right, and whew, I didn't do that one. Let's see here, 2.5 squared equals times 100. I get 625 there. All right, minus, let's see here, whoops, 320 times 2.5 minus 800. That's not good. Plus 400. All right, so let's see here. So we get 220, the square root of 225. That's what I'm getting at. And I get 15 kilometers. And so our minimum distance here is 12 kilometers after 1.6 hours is when they are the closest. All right, one more. Tough stuff, no doubt about it. All right, here we go. Example 3. A man is on an island that is 3 kilometers from shore. His favorite burger place is 3 kilometers downshore from the point on the shore closest to the island. All right. The man can paddle his canoe at a speed of 3 kilometers an hour, but he can run at a speed of 5 kilometers an hour. Determine where he should land on shore so that he can reach the burger place in the shortest amount of time. All right, so here's the situation again. I want to draw a diagram. So a man is on an island that is 3 kilometers from shore. All right, so let's draw that. Put a big I there. There's the island. All right, and here's the shore. And we'll go with it's 3 kilometers away. Maybe the shore, I'll just draw a line right across. There we go. All right, there's our shore. And again, that's 3 kilometers. All right, his favorite, so that's just the first sentence there. Then we got his favorite burger place is 3 kilometers downshore from the point closest on the shore closest to the island. So we've got 3 kilometers this way. That's 3 Ks. All right, and we've got his burger place. I will put right here. There's the burger place. Okay. So what he's going to do here is this gentleman is going to paddle his canoe to the shore at some point. He's going to hit right here, and then he's going to run. All right, so the man can paddle his canoe at 3 kilometers an hour, and he can run at a speed of 5 kilometers an hour. Determine where he should land on shore so that he can reach the burger place in the shortest time. All right, so he's going to land somewhere here. I'm going to call it X. That's this distance from straight across to where he lands. All right, now what we're trying to do here is minimize time. Now again, we have distances and speeds. So I'm going to again use my formula, V equals D over T. And I'm going to rearrange it this time, but not in terms of distance like I did the last example, in terms of time. And so to do that, I'd end up with time is equal to D over V. All right. Now, again, I'm going to use a little Pythagorean theorem here because this blue line here is kind of important because the blue line is where he paddles, and then let's go with the purple line there is where he runs. Now, this blue line has a distance because, again, I can use the Pythagorean theorem here. And, well, I have a length of 3 squared. That's not changing. Then I've got a length here of x squared for another side. And so I'm going to take 3 squared plus x squared. Then, of course, with the Pythagorean theorem at the end to find that length, you'd have to square root it. All right, and then this purple length here, if it's 3 kilometers all the way, and then you're subtracting x, that's what's left over for the maroon part, or the purple part, then that length would be 3 minus x. All right, because you have 3, and then you subtract x, and that's what you have left over. All right, now, here's where we're coming up with our time formula. Again, I'm going to use t is equal, I'm going to write that over here. T is equal to d over v. All right? Now, that blue part, the distance that they're traveling is that 3 squared, which I might as well just make a 9, plus x squared. That's the distance. Now, the velocity that this person can travel when they're paddling is 3 kilometers an hour. So I'm going to divide by 3 here. Now, the maroon part, the distance is 3 minus x. The velocity is that this person can run at 5 kilometers an hour. And so there we go. Now, that's our formula. We're trying to minimize time, which is good. We have it in terms of another variable, just one of them, which is good again, so we don't have to do any substitutions like I did in the first example. But I am going to, again, change the way this formula looks. And so I got t is equal to, before I take the derivative, I've got, let's see, I'm going to put in brackets here 1/3. Got the fraction there. I've got x squared, whoops, plus 9 to the 1/2. Again, the 1/2 represents square rooting. All right, and then plus, I'm going to break this up. So the 3 is divided by 5, and the negative x is divided by 5. So I'm going to have 3/5 minus x over 5, or 1/5 x. Same thing. All right, so now I'm going to take the derivative. So here we go. Taking the derivative, t prime. So I've got 1/3. Bring the 1/2 down, so I'm going to have to multiply 1/3 by 1/2. All right, I've got to have in my brackets x squared plus 9. Hopefully I have the room here. Subtract 1 off the exponent, so it's going to be a negative 1/2. And then there is a function inside there, so I got to take the derivative of the inside, which is just 2x. Whew. All right, so that's the derivative of that first part. Now the derivative of 3/5, sorry, is 0. And the derivative of negative 1/5 x is just negative 1/5. All right. So I'm going to simplify this thing here before I set it equal to 0. So let's see here. This 2 and this 2 here divide each other out because we got 1 in the bottom, 1 in the top. All right, and so I can simplify this. So I got t prime is equal to, the first thing I'm going to do is, let's see here, I got a 3 in the bottom, 1, 1, then an x on top. But I'm going to put this x squared plus 9 to the negative 1/2. I'm going to put it in the bottom. So again, the 1/2 is the square root. The negative sign means I can put it in the bottom. So I got x squared here, plus 9 minus 1/5. All right, there we go. All right, time to find our set our derivative equal to 0. So set t prime equal to 0. All right, so well, I might as well do that. I'm going to take a shortcut here. There's our t prime. Well, let's make it 0 here. There it is. And now I'm going to move this negative 1/5 over to the other side, so it becomes a positive 1/5. Well, I can do that just by... There we go. All right, and then I have a fraction equaling a fraction. Well, again, those of you who've been in my math class enough times, you know where I'm headed here. Let's see, cross multiplying. And so when I do that, I get 5 times x. Well, that's 5x equals this thing in the denominator times 1, which just means it's this thing in the denominator times or just itself. There we go. All right, I want to solve for x here because I want to find out where I should land on shore. Okay, so I need to get rid of the square root. So what I'm going to have to do is square root both sides. That'll get rid of the square root. It's going to change everything else as well, but squaring 5x, well, I square the 5, square the x. You got to square both. All right, so I get 25x squared. Then in the other side here, I got to square the 3 and square the square root of x squared plus 9. Well, the square root of 3 is 9. And then this just turns into x squared plus 9. All right, continuing to simplify here. So let's see here. A lot of different ways I could do this. Might as well expand that 9. So I'm going to still have my 25x squared equals 9x squared plus 81. All right, I'm going to move that 9x squared over to the other side, so it's going to be subtraction. I'm going to end up with 16x squared equals 81. Getting there, we're getting there. All right, getting x squared by itself. Before then we get x by itself, I'm going to divide both sides by 16. And so those 16s over here divide each other out, so they're gone, which is great. And then my last step here is I want to get x by itself, so I'm going to get rid of that little 2 by square rooting both sides. And end up with x is equal to, well, I know the square root of 81 is 9. The square root of 16 is 4. So it's going to be 9/4. Or, well, as a decimal, I get 2.25. And that x value, if you go back up a long time ago to our diagram, is how far upshore, which is the 2.25 kilometers. Now, I'm not sure if that's what it asks us. What do we get here? Determine where he should land on shore, so he reaches in the shortest time. Well, there you go. He should go 2.25 kilometers up the shore to minimize his time. And we could also substitute into our equation here to find the time if it was so asked, but it didn't. But just for your information, the time, because I did sub it in, was 1.4 hours. It's going to take him to get to his burger place, so it must be his favorite if it's going to take that long. But again, the question just asked how far upshore, and the answer would be 2.25 kilometers upshore would be his spot to minimize his time to go to his favorite burger place. And again, 1.4 hours there and 1.4 hours back, it better be his favorite.